Hello, everyone, and welcome to today's webinar. This is the fifth webinar that is sponsored from ASHRAE TC6.7, Solar and Other Renewable Energies. And today we have with us Ryan Danks, who will be giving a speech on simulation of PV in urban contexts. So a little bit about our speaker. Ryan is an associate principal and global practice leader for building performance and at RWDI. He leverages a wide range of simulation tools to help architects and other engineers understand how climate, people, and the things we build interact to help craft indoor spaces, buildings, and even entire cities that respond with their climate and promote efficiency and comfort. So just a couple of words for TC6.7. TC6.7 is a technical committee of ASHRAE, and we work on everything that has to do with renewable like solar and wind that is integrated into buildings. So anyone can participate. I will drop the link for anyone that would like to participate in the meetings of TC and have an active role and participate in our meetings it's 2 times a year, the meetings, and it's free for anyone that would like to be part of it. You don't need to be an ASHRAE member for it. So, and yeah, we always like to have more and more people participating in our events and our different activities. So without further ado, Ryan, you can start your presentation. Thank you for being our presenter today.
No problem. Happy to be here. Thanks for inviting me. All right. Yeah. Thanks, everybody. My name is Ryan Danks, and I am the global practice leader at RWDI for our building performance group. I came up doing a lot of solar related work, and so that was why I've been asked to speak on this topic, specifically as it pertains to kind of building integrated photovoltaics. As far as the learning objectives go for today, the goal, I hope, by the end of this talk is a better understanding of how BIPV and the built and natural environment more generally will interact and the kinds of impacts that they can create on people and property. We'll be learning some of the techniques that we can use to identify potential negative effects and also strategies for how we can mitigate those effects. Before I go any further, I do want to acknowledge the fact that while I'm the one speaking today, not everything I'm showing was done by me. I'm very lucky to work with an incredibly talented group of very, very smart colleagues. And some of this work came actually from our clients. It was driven by some of our clients who really have a forward-thinking approach to their designs and really were looking to push the envelope, which is always something worth acknowledging. Maybe one other thing to note is that today's talk is sort of an expanded and extended version of some work that had been previously presented at an ESIM conference. So that's the International Building Performance Simulation Association Canadian chapter, their biannual conference. So if there's any other technical details that people want, they can reach out to me and I can dig up that paper and make it available. So wouldn't be an engineering talk if we didn't start with an outline. And generally speaking, this presentation is in 3 parts. The first is I'm just going to kind of briefly go over the opportunities that we have with PV and with building integrated PV. I'll then move into some of the challenges associated with PV in an urban context and the different ways that we can identify the challenges if they exist and how we can overcome them to try and get the best outcome for our clients. Lastly, I'll finish up with just some concluding thoughts, and there should be plenty of time for a Q&A at the end. So we'll start right at the source. The sun is the single largest source of energy on Earth. In just an hour and a half, enough solar energy reaches the surface of the Earth to power all of human civilization for a year. 1 year's worth of solar energy is about twice as much energy that could ever be extracted from the world's supply of coal, oil, natural gas, and even uranium put together. It's kind of a mind-boggling amount of energy when you really think about it. And to put it in a little bit more context, and this is an older diagram, but it still applies. If we covered just these 6 areas in black with solar panels, we would be able to power all of human civilization. Now, obviously, this is not something that we can do feasibly, not the least of which people live in many of these spots. There's also the transmission issues and dealing with storage and all that kind of stuff. But it does really go to show how much energy we have available to us. And the good news is that some of those difficulties about this needing to be distributed have already been overcome. We've knocked down a lot of the old complaints about solar power, not the least of which was the old complaint that it was expensive. In the last decade, we have seen huge strides in both the efficiency of cells and, because of economies of scale, just the overall cost of a solar panel system just plummeting. Utility scale solar is now likely in many places the cheapest form of new energy, even when you account for some of the existing hidden subsidies for other sources of power. And even on a commercial or a residential scale, we're still seeing big drops, making it a very much a financially viable source of energy in many situations. The other old complaint that used to come up a lot was the aesthetic. People have a vision of solar panels just being these black monochromatic slabs that sit on a roof. But in recent years, we have seen thin film PV that can be curved. We've got colored PV now. We've got transparent PV or semi-transparent, so we can integrate it directly into skylights and windows. So we now, not only do we have more efficient cells, we can now integrate them better into a building and not have to compromise on aesthetics. And then, of course, there is the old refrain of, well, what happens when the sun isn't shining? But the good news is that battery technology has also made huge strides in the last several years. We have huge upticks in battery electric storage systems for utility scale solar and many options now, off the shelf consumer grade batteries for the home. It's in many places, it's no more expensive to buy a whole home backup battery than it is a traditional gas-powered generator. So all of these things coming together have really made solar panels and solar power a lot more attractive in a huge range of applications. So having said all that, you may be wondering then, well, how come we're not seeing the uptick? Why don't we see more of this? And it comes down to kind of what I like to say, the FUD, the fear, the uncertainty, and the doubt that exists around solar panels. Builders and building owners tend to be a fairly conservative bunch. They're not after anything, they're not necessarily after anything cutting edge, groundbreaking. They want to build their building for a reasonable cost and get a reasonable return on that investment, which is not unfair. But and so they hear stories online. You see just recently questions about glare, reflections from solar panels blinding air traffic controllers, or fires that are caused by them, and that makes them wary. There's also the uncertainty of the power output. When you see all the claims that the manufacturers will make, but how does that translate into real world performance, especially in an application like BIPV that is going to be much more site specific and have a lot more site specific constraints and concerns compared to an open field utility scale case. And all of these things come together to create a significant amount of doubt for a building designer. And once the ownership has these doubts, starts making PV, the PV aspect, a very ripe target for what's called value engineering, where something is too expensive and we need to start cutting costs. And really, the best way to counter a lot of these concerns is with facts. It's not necessarily about appeals to emotion or anything like that, or hoping out of the goodness of somebody's heart that they will just go ahead and do this on faith. What we need to do as professionals is help allay these fears by not hiding it, acknowledging that they exist, and understanding their potential and then mitigating them. And so that's what I'm going to step through on these next few slides, some of the common concerns about building integrated PV and how we can identify and mitigate those concerns. So the biggest issue that we see anyway is questions about solar access. Now, we have a lot of existing tools that are easy enough to look at solar energy potential on simple surfaces, exposed areas, but where we can start to run into challenges is at larger scales, if we're talking about sort of an integrated solar community, or on highly complex buildings where we where we need better fidelity on especially some of those vertical surfaces for a BIPV application, where traditional tools may not be able to have that level of detail. And it goes beyond just the existing, the building itself as well. We have to concern ourselves with neighbors. More and more, we're hearing about cases where a new building is built that negatively impacts the PV on an existing building. That's the case we're looking at here. This came from a project that I worked on, where on the small building here on the left is an existing building with some rooftop PV. And this large blue building immediately to the right of it was a proposed new development. And the owner of the PV was trying to understand how much this new building would impact their yield, and therefore how much this would impact them monetarily on their energy bill. So understanding solar access in an urban environment comes with a lot of additional complexities. But again, it's not something we need to shy away from, because we do have the tools and the understanding to mitigate, or at least understand the level of impact. And there's a few things we need to be aware of when we're studying urban solar access. And the first piece of the puzzle is kind of the spatial accuracy. Now, obviously, in any kind of 3D model of a city, you're going to have to make compromises on the level of detail of the buildings. It's just not generally feasible to study everything down to the centimeter. However, knowing where and how to make those simplifications can be really important. I've got a generic building here where I predicted the insulation on the facade, and we studied it in its exact form, so that'd be on the left, and then at various levels of simplification. And generally speaking, the total insulation, when you kind of integrate across the entire building, they were all within roughly about 4%. In most cases, that'd be okay. Depending on the financial viability, though, that 4% could matter a lot. But the bigger issue was that the size and location of the facade areas with the best PV potential change between these four cases. And that's a bigger problem, because someone could accidentally be led by this data to put their panels in a less ideal spot. And this only gets more complex as we complicate the surrounds, because now we're going to get into questions of things like microshadowing and the aggregated effect of our neighboring buildings too. So as another example of how spatial accuracy matters, here is sort of admittedly a bit of a contrived example, but it does illustrate the point. So say we have a building that is looking to integrate an awning, and they want to put PV on that awning. They have two choices. They can have this flat awning, they have a curved awning. They like the curved one better from just an aesthetic look, and they understand that there will be an energy penalty, but they want to know how much that is. How much is this aesthetic worth to them? And in order to know that, they need to know how much energy they're losing. So what we did for this case was run multiple simulations where we varied the number of test points across each of these awning elements. So we went from kind of 12 test points across the awning down to or up to over 4,000. So representing a smaller and smaller amount of area for us to integrate. And this is an example of where those subtle differences can really add up because the coarsest representation of that curved panel predicted a 3% difference. But our finest representation said that the loss was only going to be 0.6%. So that's a big enough difference that could change the thinking and change the conclusion of some of the building owners. And as I mentioned before, we're now integrating PV into things that are curved, things that are undulating. They're not just flat planar surfaces anymore. So being able to acknowledge that can be really important. And this is especially true when we're getting away from questions of how much energy lands on the panel and then and instead look at how much energy the panel will actually create. And that's because depending on the quality and the design of the panel, it can be very, very sensitive to micro shading impacts. A small amount of shadow can shade one of these cells and cut power to the entire string. Now, there are bypass diodes and microinverters and other strategies we can use to get around that, but those are expensive. So if we don't need them, we don't want to use them, and understanding where that trade-off lies is really important. And so by increasing our spatial accuracy, we can go from, estimating solar impacts at this sort of a scale all the way down, if we wanted, to the individual solar cells. And if, again, we go back to our contrived example with the awnings, and we assume our building owner did go with the flat awning, but the owner was going to cheap out and use a very cheap panel with one that was very, very sensitive to these micro shading impacts. And we rerun that analysis using the same range of test points. We find that the loss incurred by that micro shading can vary wildly. And the reason for it, in my example case, was because there's an outcropping of an adjacent building that wasn't necessarily picked up on the coarse analysis, but is on the more detailed one. And so again, understanding these micro shading impacts is a legitimate concern for a building owner, but we do have the ability to study it. And when we study it, we can understand that trade-off that we need to make of energy production versus the shape or the form of these panels or even their construction to go with ones that are more robust against micro shading. Along the same lines, we also need to think about the temporal accuracy of our simulations. How fine of a time step do we go down? This is another contrived example we're looking at here where we've got some rooftop PV and a cell phone tower. And in this case, we're going to hold the spatial accuracy of the surfaces constant. But what we're going to do is run the same annual simulation at 3 different time steps. And what we get is 3 very different patterns of where the loss in energy caused by the cell phone tower occurs. At our, industry standard, let's say, 60-minute time step, we see much deeper reductions, but they're in very discrete locations. So there's some areas that were predicted to not be affected at all of the panels, and then some areas are very, very deeply affected. And as we refine that time step, we see what you'd expect. You'd see a more smeared impact where while the total reduction stays the same, where that reduction occurs and how much each individual area of the panels are affected changes with our accuracy. And so much like our case of a the spatial accuracy. By improving our temporal accuracy, we can now understand those micro shading impacts a little bit more, and then optimize the string layout or the orientation of our panels to make them more robust against that shading. But again, this is a design trade-off that we wouldn't have been able to make in an informed way had we not modeled at that higher level of fidelity. Now, aside from solar access, there are a lot of other ways that PV and the natural environment will interact. And one of the biggest ones is wind. This can cause a lot of concern around developers because this has insurance implications. Many people do not want to drill holes in their roof for obvious reasons, but instead use ballasted PV on the roof. And so without that actual mechanical attachment, you need to be or even with that mechanical attachment, you need to have a very good understanding of the wind forces that will be acting on those panels to make sure they don't get blown off. This photo on the left is a real case that happened outside of Toronto a few years ago, where a large array was pulled right off its ballast. Thankfully, no one was hurt, but it highlights the challenges or the need to understand these wind effects, not just in terms of what happens measured at the airport, but how does the buildings around you influence the wind patterns and potentially change them. In a BIPV context, we actually need to go a little bit further, because now we need to worry about other mechanical forces acting on the buildings just in the same way we would with any other piece of cladding. So the photo on the right is from a recent windstorm down in the US, where you can see the force of the wind shattered a lot of windows. And you could imagine if these had been BIPV spandrel, something similar could have happened. So we need to start thinking about the use of PV as cladding as well, and the differences in kind of the force or the kinds of force that they're exposed to. Now, again, the good news is, while this risk does exist, again, there's ways we can study and mitigate it. Understanding wind effects on wind forces acting on ballasted or unballasted PV is something that's done very, very common, whether it's at utility scale or at rooftop scale. And in the BIPV context, we can go even further and start looking at facade elements as well. So on the left, this is a photo from a wind tunnel test conducted at RWDI for some sunshade panels. That's them in gray. And what this does is allow us to understand not just the static forces that they're being applied to, but potentially the dynamic forces as well. And this allows the designer to understand what those forces are and work with manufacturers of BIPV to make sure that it will be robust enough to act as any other normal cladding system would. And on the right, this is a computational model of wind pressures, something we do very early in a design, with the hope being that if you study it early, you can understand that risk, design it out, and then the wind tunnel test at the end is just used for confirmation to make sure everything is behaving as we'd expect. And that's kind of the ideal order for any of these studies, because you want to make sure that you're avoiding those costly redesigns down the road. Snow and ice is another common source of uncertainty when we start talking about PV. Large expanses of PV on a roof will act very much like a metal roof, in that snow and ice can build up and then shed suddenly all at once without much warning. And then suddenly you have a huge amount of snow and ice being dumped, possibly right off the roof. And then also, depending on where you are, that snow loading, the actual weight of the snow pushing down needs to be taken care of. But again, these are things that can be studied. What we're looking at here is a study from RWDI's water flume. And so essentially this is a wind tunnel, but rather than using air, it uses water. And the reason we do that is because from a qualitative perspective, the way that sand scours and flows in water is very similar to how snow will behave in air. And so this provides a useful qualitative tool to understand how snow will build up and scour from a rooftop with PV on it. You can see in the images on the right how different orientations of panels create different areas where the snow will build up or scour away. And this is important to understand from a loading perspective, because these non-uniform loads need to be taken into account when you're designing the structure of this building. But it also helps inform things like how high the panels need to be. You know, raising them up a little bit taller will help things scour away, and you don't have to worry about the panels getting slowly buried. We can also start looking at this from a quantitative standpoint using either computational techniques or, again, physical modeling. So the photo on the left there is from what's called a climatic wind tunnel, where not only are you able to adjust wind speed, but you can adjust temperature, you can introduce solar radiation, you can introduce rain, snow, ice, and it allows you to study at full scale building details, including things like building integrated PV panels. So whether that's on the spandrel, whether you're using it as sunshades, vertical or horizontal, there is the ability to study how snow will build up and shed from these different elements that can help allay fears around snow and ice falling from some of these elements. Reflections and glare are another very common source of fear when it comes to PV. You know, there have been a lot of famous cases that make the news, and this, when we do utility scale work, this is the number one concern that neighbors always have is will these cause glare? And it's important to acknowledge the fact that while PV is designed to absorb as much light as possible, the outer surface is usually still glass. And when light hits glass at very glancing angles, it will become more reflective, and so a lot more light will leave the panel when the light's hitting it at those glancing angles. And so when we start putting PV on building sides, that condition can happen a lot more often than when they are more horizontally oriented. So the photos on the screen here came from an airport in New Hampshire and back in 2013, they had a real problem when they installed some solar panels on the roof of a parking garage. And it was blinding the air traffic controllers. They couldn't see the taxiway, which is a fairly busy part of any airport. Ultimately, this led to a lot of money being spent to identify the problem and then eventually mitigate it, which was to physically rotate the panels so that the reflections would miss the tower. Since this issue arose, the American FAA, the Federal Aviation Administration, rewrote their rules around PV on airport properties, which are now generally accepted elsewhere around the world, and then other places have extended it as well for non-airport operations. So just any sort of utility scale or large scale PV is required to do a glare study in several Canadian provinces, many US states, and regulated federally in Germany and Austria. As I mentioned near the beginning, Schiphol Airport in Amsterdam, that country's busiest airport, recently had to shut down some of their runways because of the reflections from PV. And I think the last I read that the solution was going to be that they need to remove about 5,000 panels to make this issue go away. So this can be a very dramatic and very potentially dangerous situation, even in a BIPV context, because now we have drivers, and you have a lot more drivers on a road than you at rush hour than you probably do airplanes landing on a runway. But again, something to be aware of, but not something to be overly afraid of, because we can predict when this happens and there are solutions. It The image in the upper left shows some deeply textured panels, which act to not only drive more light to the cells itself, improving the efficiency of the panels, but also they act to scatter and diffuse any reflected light, so it's less bright for an observer. The photo on the right is an example of an early design study we conducted for a helipad. So that blue volume there indicates the approach paths for the helicopters. The helipad's kind of in the middle, and that purple blob around there indicates how far potentially glare-causing reflections could travel from the PV panels that were planned for this roof. And so by understanding the problem, what we were able to do is define when and how often this could occur, and then allow the local air safety authorities and the owners to understand what could happen and come to a compromise with all the context. And ultimately what was done, because the risks of glare were limited to only kind of very specific periods of time, it was they didn't end up removing or changing the design, but it was more just a general bulletin for pilots to be aware of who are using this private helipad. So again, we have the ability to understand the problem and the ability to prevent it. Heating and fire, this is another concern, though not as common until something goes wrong. Most panels are generally on the order of 15–20% efficient, which means the rest of that energy is getting turned into heat. PV systems can easily hit 40, maybe as high as 80 degrees in the summer, depending on where you are in the world. And the challenge with PV is that the hotter the cells get, the less efficient they are, which in turn make them hotter. So you get into this vicious cycle where as they get warmer, they get less efficient, and they get hotter and hotter and hotter. And in some cases where the connections between the cells break and individual cells get extremely hot, then you can start seeing fires. Or in the case of a BIPV application, you could have panels that are getting much, much hotter than someone working next to them might expect. You could imagine a window washer on the outside of a building, or even someone working on a rooftop adjacent to some PV or a terrace. It's important to be aware of how hot those can get and make sure that they don't come into contact with it and get burned. Or more broadly, we want to make sure that heat isn't being re-entrained into the building. You don't want to have an air conditioner right next to a really hot surface now it's got to work harder because it's sucking in hotter air than you would have expected. But again, we have tools that we can use to deal with all these issues. It is possible using computational fluid dynamics to start looking at how hot systems will get, where that heat will go, and the risk of mechanical systems ingesting a lot of that heat. And then we also have solutions. There are PVT systems, so photovoltaic thermal systems, where we're actually leveraging the fact that the PV gets hot to create hot water. And that can be then used for heating or domestic hot water. I've even seen some newer techniques that actually try to recover that waste heat and turn it back into energy with thermocouples and that sort of thing. And it does provide, there are a lot of solutions out there so long as we identify the problem early on. The last big challenge that I'll touch on is maybe a more global one, because really this applies to any sort of study of a PV system anywhere in the world, and that is the reliability of your climate data inputs. There are a lot of sources of climate data out there. Some are better than others, and you need to understand which ones are good for different types of studies, because not all of them are created equal. So this is going to present a little bit of work from that 2018 paper, where we looked at the impact of our MET choice for a project in Boston. So that's what we're looking at here. This green area, that's Boston Common, a large park in the center of the city. So we're going to be looking at surface level irradiance, but obviously this would apply just as well to any any building integrated applications as well. So generally speaking, when we look to climate data, I think most people just kind of look for the closest Met station that has a typical year file or an EPW from another source, and we use that. Now, aside from the challenges of understanding what happens when you're smack in the middle of two, or maybe there's an obstacle between your site and the station, even just the use of that typical year data, we need to be a little bit careful with. So we're going to start with something simple. So what we're looking at here is the total annual insolation on Boston Common predicted using two different sources of data. The one is the TMY3, the typical year file for Boston Logan International Airport. And in the center, we're using a 20-year period of data from the National Renewable Energy Lab that's site specific. So this is satellite measured data that NREL makes available. And what we're able to see right off the bat is that the results are pretty close. On average, the TMY file looks to be under predicting by about 6% compared to the NREL satellite data. Maybe not a huge deal, but again, in a BIPV application, because of how expensive that often can be, you want to make sure you're accounting for every single watt. Like that 6% could matter, maybe. And then across the park, the range of difference kind of is on the order of 3, 6, maybe up to 9 in some spots % difference over relatively short distances, which again isn't great. But I think in terms of the total annual insolation, not the worst comparison in the world between these two data sources. But we still need to be careful depending on what we're trying to do, because sometimes we're not just worried about the annual insolation in total. So here's the same two data sets, but this time what we did was add a proposed building to the model and predicted how much energy is lost on the park because of that new building. And now what we see is a much more dramatic change in the two results. The TMY file predicts a much smaller area of impact, but the impact is a lot larger. But probably what's a little bit more problematic about this is just how quickly the predictions change as you move around. There's some spots here where we go from a 50% under prediction to a 50% over prediction of the impact of this building over the span of about 15-20 meters. And so if we were looking at these more detailed shadow impacts, this could lead to something. We could accidentally predict an incorrect amount of energy loss. And if there's any sort of compensation happening, because we had PV here and this new building was trying to be a good neighbor and compensate us for that, we could be off very, very by a lot. And how much we're off will depend on where our PV happens to be relative to this building. And then, even in other cases, it could mean we move the system into the wrong spot. So neither of which are really great outcomes. So I guess the question then is, well, why does this happen? So one aspect of this is cloud cover. So the typical year file is typical in the sense of a specific weighting algorithm that looks through many years of data, and out of all those years, it picks the specific January that is the most representative of all the other Januaries. And then it repeats that process for all the other months. So you have a synthetic year of data that in terms of its monthly and annual statistics is typical for where you are. The problem is any individual hour or day in that file is not typical at all, and it shouldn't be expected to be, because that's not really what these typical year files were for. These BPWs and TMYs were originally created for building energy modeling. So they don't necessarily care so much at trends at that low of a time step. They are worried about the bigger picture changes in terms of the total amount of radiation, not that hour-to-hour variance. That's why the previous slide showed a much better match than what we're seeing here, because the cloud cover that's happening hour to hour can't be considered typical. And because our building is only going to be shadowing during specific times, we could be under or over predicting just because that one or couple of hours happened to be cloudy or happened to be clear in the Met record. With the longer term NREL data, we move away from that and start being able to look at things a little bit more statistically. Over that 20-year period, we're going to be capturing a lot more different sky conditions, and we're less likely to bias our results just because a certain range of them could be influenced by cloud. The larger issue, though, is what I showed a few slides back with our cell phone tower example. Typical year files are hourly. NREL data can be at a time step as low as 5 or 10 minutes. So we have a much improved temporal accuracy, which, as we saw in that previous slide, helps us reduce the risk of overstating some impacts and missing others. Depending on the time of year, the sun can move fairly quickly in an hour. And it is definitely possible to completely miss some shadow impacts. And then the shadow impacts we do catch are going to be exaggerated because of that coarse time step. That whole hour's worth of sun loss is happening in one spot rather than getting smeared around as it would be with a more refined data set. And this can even be worse for other parameters that we need to be thinking about too, for some of these other interactions between PV and the natural world. So what I've got here on the screen is data from Toronto. So at the top, that's data, 20 years worth of data taken at Toronto's main airport, Pearson. And then at the bottom, the typical year file. Now, if we look on the left and we compare the temperature statistics, we see that they are generally pretty close. And you would expect that to be the case because temperature is weighted very highly in that algorithm that defines what's typical in a typical year file. But other parameters are not weighted so highly, especially parameters like wind. So on the left, I've got two diagrams here that are called wind roses. So for those that aren't familiar, what this wind rose is showing is the frequency and intensity at which wind blows from different directions. So if we look in the upper wind rose for the full airport data set, we see wind blows most frequently. In this case, I've clipped it to just the winter months. Most frequently from the winter, in the winter, it blows from the north to about the northwest, and it can be fairly strong out of those directions. Now, we compare the real airport data to the TMY, and we see two very different wind patterns. And that is for a couple of reasons. The first is, like I said, the typical year file doesn't rate wind very highly in terms of what's typical. So there's no guarantee that even the full year data would be typical, or at least might be at least closer. But the issue here is that by limiting it to just the winter months, we expose another flaw similar to with our solar data. We just don't have enough data. We just don't have enough hours once we've clipped it to understand or to get the proper statistics. Between the low rating and the low number of data points, our results are just kind of all over the place compared to if we had used a longer term record. And now these sorts of parameters can become very important if you're worried about things like the heating of solar panels, right? Like that cooling capacity of the air is something that's very important to understand if you're worried about how hot they could get and where that heat may go. Same with snow and ice. We need to understand how often and how strong wind blows from different directions to know how that snow will build up or scour from a rooftop. So we need to be very, very careful when we're talking about these typical year files. And to be clear, I am not trying to knock the use of them. These are very, very useful. They're ubiquitous in the building simulation industry, and they do have a useful purpose. The problem only arises when people don't understand the assumptions and the limitations of these files, and they try to use them in ways that they were never intended to be used for. And now we are starting to see a move to kind of make that limitation a little bit more clear. So the NREL data set I mentioned, other groups are also producing TDYs and TGYs. So those would be typical year files where the weighting for global radiation or direct normal radiation is weighted much, much higher. So you start getting a much more reliable source of solar data. And then there are similar ones, TWYs, which are focused on the wind parameters that some other organizations are putting out, where they change the weighting factors in the algorithm to make files that are more appropriate for a given application. However, if you're trying to look at things holistically and understand sort of the interplay of wind and sun and temperature, then there really is no substitute for long-term historic meteorological data. I know that that's often challenging in some existing tools, but there really can be value to it if you want to sort of narrow that uncertainty and really sharpen your pencil and help clients understand these nuances in a little bit more detail, especially if they're asking about, well, how often could this happen? That would be something that would be very tricky to say with an analysis just of a typical year file. Having a long-term 20 years of historic MET, on the other hand, makes that ability to talk about frequencies of occurrence a little bit easier. So I wanted to make sure we had plenty of time for questions. So I think I'm going to just kind of end with some concluding thoughts here. So integrating photovoltaics into our building stock is a tremendous opportunity. It reduces our greenhouse gas emissions. It improves the resilience of our buildings in a changing world. It makes them more energy independent and able to function well regardless of what's happening elsewhere. However, the large-scale adoption of PV technology does seem to be lagging, and in my opinion, it's because of this FUD, the fear, the uncertainty, and the doubt. And a lot of this is driven by emotion. And so the best way to counter an emotional response is with facts. And I think that is the burden on all of us as architects, as engineers. It's to make sure we aren't, sweeping these problems under the rug. We need to acknowledge them head on, but also acknowledge the fact that they can be predicted and they can be mitigated. And one of the best ways to do this is through doing deeper analyses, making sure we are identifying those micro shadowing impacts. We are assessing the risks for snow and ice, and we're doing all of this as early as possible in the design process. This if BIPV or PV more generally is being planned for a project, it should be something that's thought about from day one. As that pencil hits the paper. We have tech tools exist for quick upfront studies that can help identify things like cladding loads, like wind conditions around a building, and this can help guide the design all the way through. And then later on, during, if regulators get involved, or if you want that final level of confidence, then you can take it to the next step with more detailed computational tools, or even wind tunnel testing. And by arming ourselves with this information, we're able to fight back the fear with facts. And that can go a long way to allaying concerns and hopefully making more of the PV survive its the value engineering process, so it actually gets implemented into buildings. And the more buildings we get, the more people will get comfortable with it, and we'll start seeing that snowball effect where more and more of this will happen. And by doing all this well, we'll end up with more resilient cities, lower greenhouse gas emissions, and just generally more independent structures that can serve the people who live and work in them. And on that note, maybe I will stop there, and I can open it up for the Q&A. Thank you.
Thanks so much, Ryan. I like your optimistic view at the end. Hopefully we see more and more BIPV, especially in Canada. Yeah, I'd like to start some questions myself, so we start the roll. So first I wanted to ask, you mentioned in a slide the different cells, different solar cells that are possible, the graph with the efficiency that's going up. So I wanted to ask, in the industry and your experience, have you seen any projects where they apply different types of cells besides silicon, or is this still in the research stage?
I have not seen anything non-silicon, no. I think that's still, as I mentioned before, I think a lot of developers, like this is already new technology for the building environment. And I think that extra layer of uncertainty beyond something that's already been tried and tested at utility scale, I think that puts a lot of people off.
Mm-hmm. Yeah, okay, yeah, that makes sense. Yeah, okay. My next question was on you showed a couple of slides where you were showing the different detail and how this would change the prediction of the production, or like with the curved. So I would assume there's a way to connect like the detail level with your design stage, right? So in earlier design stages, you'd have lower levels of detail, but as you showed, the level of detail will can make a big difference on your decision making. So how could the designer decide what the level of detail is at the early design stages, if that means that you could possibly make the wrong decision because you didn't put enough detail in it?
Yeah, I mean, it's a difficult question to answer, but it mostly depends, I would say, on your on the site surroundings. If you are, so that awning in that case, that's a fairly tight urban corridor. That's something where you maybe want to start a little bit more detailed, especially if you're doing something curved or non-flat, or if you have other things nearby, even if it's not a building, other things that could potentially generate those micro shadowing impacts. So I think someone who's experienced in this would be able to even just look at a design or a 3D model or some drawings, and would have at least an inkling of how detailed they should be going at that first step.
Yeah. Yeah. And another question I had was about, I don't know if you're familiar with, because you talked about the wind effects and the whole PV that came off from that building. So is there, for BIPV specifically, so that it would be part of a building pretty permanently if we decide to put a PV on the building? Are there insurance issues with that? Like, are insurance companies willing to insure, like to put an insurance on if a designer decides to put PV on a building and it's not a typical like building product, it's kind of custom?
I haven't personally come across any with respect to insurance concerns. I think generally speaking, you're treating it, as far as my work goes, we'd be treating it as we would any other piece of cladding, just to understand wind forces and heat in some cases coming off them or being generated by them. I imagine where the insurance would come in more strongly would be on the electrical side and those connections, and that's something that I don't really get involved in.
Okay, yeah, good to know. We have a question from Zelalem Abebe. So they write, thank you, great presentation. Have you come across any buildings featuring BIPVT systems that use water or refrigerant-based PV cooling while also utilizing the generated heat for the building's heating demand? How feasible do you think this technology will be for future buildings?
That's another very good question. I haven't personally seen any in a BIPV state. I've worked on a couple of designs where it was a more traditional roof-mounted system. And the reason there is just for the ease of the plumbing, right? You could imagine that if it was a BIPV, depending on how it is distributed and where it's distributed, getting the refrigerant to it or the working fluid, whatever it is, could be really difficult and potentially, well, almost certainly very expensive. So where I have seen them even suggested is usually in a more centralized place where all your panels are in one area, so your pipe runs are shorter, and then that feeds down. In that case, it could work. I'm not familiar with any that are actually built yet, though. I think a lot of the time it's the closest I've seen was it was almost a double skin facade sort of setup where the BIPV was the outer level, and then you had clear glass on the inside, and that interstitial space was heated up, and that was used in the winter, or in the summer it was just opened up and allowed to evacuate.
There, I could add on that that we in my research lab there are some projects that are air-based BIPVT. So because it's air, it's a little bit more easy maintenance-wise. So there, an example is on the campus at Concordia University in Montreal. There is the GMSB building, that is the business school. So there is a BIPVT that works, and it uses the air for preheated ventilation air. And then there's one more building that I'm familiar with that is it's the Varennes Library. It's a library at the suburbs of Montreal, and that also is air-based BIPVT that uses ERV. But yeah, those are two that I know. And lastly, my last question, but I please the audience could also add more. I also have a question on climate change on the weather. Is there a way to account for climate change into our weather files in our simulations?
Yeah, that is another one that is a real can of worms once you start trying to look into it. Because, as you can imagine, simulating the entire planet decades into the future is a non-trivial kind of thing to do. The current climate models do provide some good reliable results in terms of temperature change, and more recently, good higher confidence in the humidity changes that we'd be expecting. But because PV relies on cloud cover, aerosols, all this other stuff that is much more difficult to try to predict. Generally speaking, we will tend to use historic data rather than try to guess at what's happening going forward. A lot of the warped weather files that you see some of them are just as simple as taking the existing TMY and then adding 5 degrees to everything, or 3 degrees or whatever to all the temperatures, and then adjusting the humidity accordingly. So they're not even actually warping things like solar or clouds, because there's no real good basis for how to do that. I think I was in at the last ASHRAE conference in Orlando. I was sitting in on one of the climate change seminars. And I wish I could remember the name of the individual who said it, but he said there's a reason why all the universities that put out the warped climate data always call it beta or experimental or things like that. It's to make it clear that this is kind of, use at your own risk, kind of a best guess kind of thing, rather than hard details.
There's too much uncertainty, kind of.
Yeah. So and I mean, I think it goes back to the question of, do you even need the climate change data? Like, how much do we expect cloud cover to change?
But about well, about the temperature though, or
Yeah, temperature for sure it could be an issue. But I think again, when you're looking at BIPV, it's temperature, but it's also wind, it's also solar exposure. It's a
yeah.
combination of things. So unless you have a good handle on all three, it gets a little tricky. In some applications. I mean, there may be others where, you know, just assuming it's 3 degrees warmer is fine, and it's not going to dramatically change things. And then, yeah, then you can just base that on the current projections with good reliability.
Okay, that makes sense. Yeah. Are there any other questions? If not, we could wrap up a little bit earlier. Oh, okay. Here we have one more. Thank you, Ryan and Anna. Thank you for being here. What industry software can we use to evaluate BIPV in urban areas, such for BIPV facade micro shading?
So most of what I showed today was computed using some custom software that we've built over the years to give us the flexibility to look at those sorts of scales. But I mean, there's lots of software out there. There's you know all the various Rhino plugins that exist. There are for and that could potentially get down to that level of detail to look at micro shading. I can't say that I have tried to do them at that sort of a scale, but there are tools out there that could be or potentially could be adapted to look at that scale of space or time or both.
Yeah, and also I think now with there's also Python plugins for almost everything,
Yeah.
so you can customize a lot of stuff.
Yeah, if you want to get your hands dirty and dig into and actually write your own code, yeah, there's lots of stuff in Python and even some C libraries to help out with that.
If we don't have any other questions, maybe we could wrap up. Thank you, Ryan, so much for your presentation. It was really very interesting, and it was on many different topics on PV. I'm hoping we get to see more and more projects on BIPV, PV and BIPV, and it becomes the norm soon.
Yeah.
And I hope to see you in the next webinars, everyone. And yeah, thank you for attending. That's it. Have a good day.
Thanks, everyone. Have a good day.